Grounding is a critical aspect of electrical safety, particularly when dealing with subpoles in detached structures such as garages. Let's explore the correct grounding procedures for a subpanel located in a detached garage, focusing on the use of the green bonding screw and the bonding of the neutral and ground conductors, both when an equipment ground is present and when it is absent. We will start with the scenario where an equipment ground is pulled from the main panel to the subpanel. In this case, the green bonding screw on the subpanel should be used to bond the equipment ground to the enclosure of the panel board. The purpose of this bond is to create a continuous grounding path back to the main panel. This continuous path is crucial for ensuring that any fault current has a low impedance path back to the source, allowing overcurrent protection devices such as circuit breakers to trip and clear the fault quickly. Without a proper grounding path, fault currents could linger, posing a significant shock hazard. Now let's discuss the neutral and ground bonding in this scenario. With an equipment ground present, the neutral and ground should not be bonded together at the subpanel. The reason for this is that the equipment ground now serves as the designated grounding path. Bonding the neutral to the ground at the subpanel would create an improper parallel path for current flow. This parallel path can lead to several problems. Firstly, it can cause neutral current to flow on the equipment grounding conductors, which is undesirable. Secondly, it can create ground loops, which can introduce noise and interference into sensitive electronic equipment. Thirdly, it violates the National Electrical Code, specifically Section 250.32b, which prohibits bonding the neutral and ground at a detached building when an equipment grounding conductor is run with the feeder. Next, let's consider the scenario where no equipment ground is pulled from the main panel to the subpanel. In this case, the grounding procedure changes significantly. Firstly, the green bonding screw on the subpanel should not be used. This is because there is no equipment grounding conductor to bond to the enclosure. Without an equipment grounding conductor, bonding the enclosure to the neutral would create a hazardous situation, as the enclosure would become energized under certain fault conditions. Now let's discuss the neutral and ground bonding in this scenario. In the absence of an equipment ground, the neutral and ground should be bonded together at the subpanel. This bonding is necessary to ensure a proper grounding path for the subpanel and its connected loads. The neutral conductor, in this case, serves as both the neutral current carrying conductor and the grounding conductor. By bonding the neutral to the enclosure, you create a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate. This practice is permitted under the National Electrical Code Section 250.32 when an equipment grounding conductor is not run with the feeder to the detached building. It's important to note that this method relies on the neutral conductor's integrity to provide a safe grounding path. Therefore, the neutral conductor must be properly sized and installed to handle potential fault currents. Consider that if metal conduit is used to run the feeder cables between the main panel and the subpanel, it can also serve as an additional grounding path. In this case, the metal conduit should be bonded to the subpanel enclosure, regardless of whether an equipment ground is pulled from the main panel. The metal conduit provides a redundant grounding path, enhancing the overall safety of the electrical system. Bonding the conduit ensures that it is at the same potential as the other grounding conductors, preventing voltage differences that could lead to corrosion or shock hazards. Maintaining proper grounding practices throughout the electrical system is paramount to ensure safety and the proper operation of electrical equipment. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to operate and clear the fault. Without proper grounding, fault currents can create shock hazards, damage equipment, and even cause fires. Therefore, it is essential to follow all applicable codes and standards when installing and maintaining electrical systems. Remember to consult the National Electrical Code or a qualified electrician for specific requirements and guidance. To further illustrate the importance of these grounding principles, let's delve into some practical examples and common scenarios that electricians encounter in the field. Imagine a situation where you have a detached garage with a subpanel and an equipment grounding conductor is properly installed between the main panel and the subpanel. In this case, the green bonding screw is used to bond the equipment ground to the subpanel enclosure, and the neutral and ground are kept separate. Now, suppose a fault occurs in a piece of equipment connected to a circuit in the subpanel. Fault current will flow through the equipment grounding conductor back to the main panel, tripping the circuit breaker and energizing the circuit. Because the neutral and ground are kept separate, fault current does not flow through the neutral conductor, preventing any potential voltage rise on the neutral and minimizing the risk of electric shock. Now let's consider a different scenario where there is no equipment grounding conductor between the main panel and the subpanel. In this case, the neutral and ground are bonded together at the subpanel and the green bonding screw is not used. Suppose a similar fault occurs in a piece of equipment connected to a circuit in the subpanel. The fault current will flow through the neutral conductor back to the main panel, tripping the circuit breaker and energizing the circuit. Because the neutral and ground are bonded together, the enclosure of the subpanel is effectively grounded, providing a low impedance path for fault current to flow. However, it is crucial to ensure that the neutral conductor is properly sized to handle the potential fault current. If the neutral conductor is undersized, it could overheat and create a fire hazard. In addition to these basic grounding principles, there are several other considerations that electricians should keep in mind when grounding subpanels in detached structures. Firstly, it is essential to use the correct size of grounding conductors. The size of the grounding conductors must be adequate to handle the potential fault current. The National Electrical Code provides tables that specify the minimum size of grounding conductors based on the size of the overcurrent protection device. Secondly, it is important to properly terminate grounding conductors. Grounding conductors must be securely connected to the grounding electrodes and equipment enclosures. Loose or corroded connections can significantly increase the impedance of the grounding path, reducing its effectiveness. Thirdly, it is crucial to protect grounding conductors from physical damage. Grounding conductors should be installed in a manner that protects them from damage from impact, abrasion, or corrosion. Damaged grounding conductors can compromise the integrity of the grounding system. Another important consideration is the use of ground fault circuit interrupters, commonly known as GFCIs. GFCIs are devices that detect small imbalances in current between the hot and neutral conductors and quickly de-energize the circuit. GFCIs are particularly effective at preventing electric shock injuries in wet or damp locations, such as bathrooms, kitchens, and outdoor areas. The National Electrical Code requires GFCIs to be installed in many locations to provide enhanced safety. In addition to GFCIs, arc fault circuit interrupters, commonly known as FCIs, are another type of circuit breaker that can help to prevent electrical fires. FCIs detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur due to damaged wiring, loose connections, or faulty appliances. FCIs are required in many circuits in residential dwellings to provide enhanced fire protection. It's also worth noting the importance of regular maintenance and inspection of electrical systems. Over time, electrical connections can loosen, insulation can deteriorate, and equipment can fail. Regular maintenance and inspection can help to identify and correct potential problems before they become serious hazards. A qualified electrician should perform electrical inspections at least every 3 years to ensure that the electrical system is safe and in good working order. In conclusion, proper grounding is essential for electrical safety. When installing a subpanel in a detached garage, it is crucial to follow the correct grounding procedures based on whether an equipment ground is present or absent. Always consult the National Electrical Code or a qualified electrician for specific requirements and guidance. By adhering to these principles and practices, you can ensure a safe and reliable electrical system for your detached garage. Furthermore, consider the importance of surge protection. Electrical surges can damage sensitive electronic equipment such as computers, televisions, and appliances. Surge protection devices, commonly known as surge suppressors, can help to protect equipment from damage caused by electrical surges. Surge suppressors are available in various forms, including whole-house surge protectors and plug-in surge protectors. Whole-house surge protectors are installed at the main electrical panel and provide protection for the entire electrical system. Plug-in surge protectors are plugged into individual outlets and provide protection for equipment connected to those outlets. The National Electrical Code requires surge protection in certain applications to enhance the safety and reliability of electrical systems. Another consideration is the use of proper wiring methods. The National Electrical Code specifies the types of wiring methods that are permitted for various applications. It is important to use the correct type of wiring for the intended use. For example, in wet or damp locations, such as outdoor areas or bathrooms, it is necessary to use wiring that is rated for wet locations. This type of wiring is designed to resist moisture and prevent electrical shorts. Similarly, in areas where wiring may be exposed to physical damage, it is necessary to use wiring that is protected by conduit or other means. Understanding the principles of electrical bonding is crucial for ensuring electrical safety. Bonding is the process of connecting all metal parts of an electrical system together to create a continuous electrical path. This path provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to operate. Bonding is particularly important in areas where there is a risk of electric shock, such as bathrooms and kitchens. The National Electrical Code specifies the bonding requirements for various electrical systems. In addition to bonding, grounding electrodes are an essential component of a grounding system. Grounding electrodes are conductive rods, plates, or wires that are buried in the earth to provide a connection to ground. The grounding electrode provides a low impedance path for fault current to flow to ground, helping to protect people and equipment from electrical shock. The National Electrical Code specifies the types and sizes of grounding electrodes that are permitted for various applications. Consider that electrical systems are constantly evolving and new technologies are being developed all the time. It is important for electricians to stay up to date on the latest codes, standards, and best practices. Continuing education courses and professional certifications can help electricians to maintain their knowledge and skills. By staying informed and continuously improving their skills, electricians can ensure that they are providing the safest and most reliable electrical services possible. Finally, never underestimate the importance of safety precautions when working with electrical systems. Electricity can be dangerous, and even a small mistake can have serious consequences. Always follow proper safety procedures, wear appropriate personal protective equipment, and energize circuits before working on them. If you are not comfortable working with electricity, it is always best to hire a qualified electrician. In summary, grounding is a multifaceted and critical aspect of electrical safety. From understanding the proper use of green bonding screws and neutral ground bonding in subpanels to considering metal conduit as a grounding path, surge protection, appropriate wiring methods, bonding techniques, grounding electrodes, and continuous professional development, every element contributes to a safe and reliable electrical system. Adhering to the National Electrical Code, staying informed about technological advancements, and prioritizing safety precautions are essential practices for all electrical professionals and anyone working with electrical systems.